So welcome to Math 150. This is lecture 20. So today we're going to be doing tangent planes, approximations of functions, and directional derivatives. So there is two sections of homework for today, but it is not due next class. So it is due on Monday, not on Friday. What I want to do is I want to try to alternate. It's not going to be a one-to-one alternation between developing theory and doing applications of theory. You're answering the questions, why are you taking this class other than just checking a box? This is a prerequisite for other things. What can you do with the material that we're developing? So I want to spend Friday talking about some of the applications of calculus. What I will often do both in the applications as well as in the developing of the theories is I will frequently focus on simpler examples that really illustrate what's going on. So a lot of the calculations we do, a lot of the proofs we do might be more focused on the one-dimensional case rather than the several dimensions. Okay, and so the beginning today is to talk about what does it mean for a function of several variables to be differentiable. So we talked earlier in the semester that there were three definitions of the derivative. And we said that not all of these definitions generalize as well as others. And it was the third definition that generalized well for functions of several variables. We talked about how it's not enough for the partial derivatives to exist for the function to be differentiable. It's a necessary condition, but it's not a sufficient condition. And we said that one way of looking at the definition of the derivative in one variable is that a function of one variable is differentiable if the tangent line does an excellent job approximating the function near the point we care about. And the generalization to functions of two variables is that, well, the tangent plane, which is the generalization of the tangent line, should do a really good job of approximating the function near the point we care about. And as you go to more and more variables, then it becomes the tangent hyperplane. And that's going to be our definition of the derivative. The tangent hyperplane does such a good job of approximating that when you subtract where you are from where you think you should be, your approximation, it's so close that even when you divide by how much you move, it's going to be small. So imagine I am obeying the speed limit and I'm traveling at, say, 65 miles per hour on a highway. Can you predict where I'm going to be a second later with high accuracy? Yes or no? Second later. Have I moved that much? No. If you just said, well, you're where you were, that's not a horrible approximation. We can do better. And we can say, let's assume my speed is constant for that entire second. And we can use that to make an approximation. It will be a better approximation as to where I'll be. The difference is not going to be tremendous. But if we now look at the difference between where we are and where we predict in the two different methods, and we divide that by the elapsed time, now all of a sudden there's a huge difference between the two of them. And that's what's really going on, is we want to have approximations that are so good that when we divide by the small amount of time we move by, it's going to be very accurate. All right, so here's just, graphically, just here, the blue is some function z equals f of xy. So we have a function of two variables, and we'll let z be the height. So above each point in the xy plane, we go up to height z equals f of xy. And we have some point p, and we draw the tangent plane. And if the function is differentiable at p, near that point p, the function should be well approximated by that plane. So again, what were the three different definitions? We had, oh, that's right, I forget. I have to always change the font size. So we have, f prime of x was the limit as h goes to 0 of f of x plus h minus f of x over h. That was the first one. Then we could say, well, f prime at some point a was the limit as x goes to a of f of x minus f of a over x minus a. And another way of saying this is that the limit as x goes to a of f of x minus f of a minus f prime of a x minus a over x minus a equals 0. And if you look at what's going on in the third one, f of x is where we are at time x. F of a is where we started. F prime of a is our instantaneous speed. X minus a is the elapsed time. And so we're looking at the difference between where we are and where we approximate where we would be using the straight line. And we're saying it has to be so good that even when we divide by that small amount of time that we've moved by, it's going to tend to 0. Again, it's not a big deal to have a close approximation on a relative scale when the elapsed time is extremely small. 1 second later, I'm traveling 65 miles. My distance doesn't change that much. It's how is my approximation relative to how much time has elapsed. And so what we're doing here is, if this is my function, and here's the point I care about, I'm replacing the function locally with what's going on with that straight line. And then the generalization for several variables would be the limit as x goes to a of f of x minus f of a minus the gradient of f at a times the vector x minus a. So it's going to be a dot product divided by the length of x minus a, and that should be 0. So that is our generalization of the derivative. So f of x is where are we at time x? F of a is where we start. The gradient of f is the generalization of how we're changing. It's the generalization of our speed. It's our speed vector. X minus a is the direction we've moved. And then we take the dot product, and that's going to give us a number. So the numerator is a number. X minus a, that's how far we've moved. Okay, well, when we look at how far we've moved, that's now a vector. And so we really have to divide by the length of that. We can't divide a number by a vector. If you look at what we had, oops, this is probably what I'm trying to get in. Hello? All right, thank you. I will see what I can do, but I'm not optimistic. Thank you. All right, we're getting some audio issues in Zoom. I thought the audio was joined because he said the audio was okay. Now it says it's working now. One of the solutions sometimes is the disconnect will work. No, it's joined. I don't want the computer to join. I want it. The audio is no. The audio was always joined from the iPad. So let me just check and see if they're saying it's okay. Okay, good. They're saying it's working now. Okay. So when we're looking at the definition of the derivative in one dimension, I could put, if I wanted to, I could put an absolute value over it. For real numbers, it doesn't make much of a difference. If something goes to 0, its absolute value also goes to 0. And then just to have things a little bit more similar, I could have the absolute value in the numerator, and I could have the length in the denominator, just to make things look as similar as possible from the one-dimensional and the several-dimensional case. So sometimes you have to just be a little bit careful about how we're approximating. So we talked about why this is the natural definition of the derivative, and we can see that this is the generalization of the tangent line. It becomes the tangent plane or the tangent hyperplane. And so just as a reminder, there's several different ways of writing the equation of a plane. And the reason we care so much about this is the whole idea, one of the two big ideas of calculus is you take something complicated and you replace it with something simpler. In one dimension, you replace a complicated function with a straight line. In 2 dimensions, you replace a complicated function with a plane. And so if I give you a normal, then the plane is all vectors perpendicular to that normal going through a base point. Or I could give you 2 directions, and it's going to be all vectors, your base at some point in a linear combination of those 2 directions. Depending on what information I give you, different ways are going to be more convenient to write. You should remember there's at least 3 different equations of a line that you hopefully learned in some algebra class. If I give you point slope, which version should you use? Point slope form, right? If I give you slope-intercept, you should probably use the slope-intercept form. And it's not bad to convert from one to the other, but depending on what you have, sometimes one version is easier to use than the other. So depending on what I give you, different forms are a little bit easier to use than others. If you look at the first boxed equation, so we're looking at the function z equals f of xy. So my height is going to be the function of x and y. So I have a function of two variables, and I can graphically represent this in three-dimensional space as z is just going to be how high up I'm going. This is similar to in one dimension, you'll have y equals f of x. You give me an input x, f of x is how high up I'm going. And so here is the approximation. So I have my point f of AB, so I'm trying to go at the point AB, and f of AB is just where I start. And then f sub x of AB is the partial derivative of f in the direction of x. And then I'm multiplying that by x minus a. I'm multiplying it by how much have I moved in the x direction. And then I add the partial derivative with respect to y at AB times y minus b, which is how much I've moved in the y direction. And so that's going to be the tangent plane. What's nice is this is clear how it would generalize if we had more variables. You would just add more partials times how much you've moved in each direction. And one way you can see that this is reasonable is if I keep in 2 dimensions, if I keep y fixed, I've reduced it to a one-dimensional problem, it should reduce back down to the tangent line. Similarly, if I keep x fixed, it should reduce to the tangent line, but now in the y direction. And so this is the only thing it could possibly be. This is what's going to constantly reduce downward. We can use this to approximate functions. If I know the value of the function at some point AB, and I know the partial derivatives at AB, I can then approximate, well, let's move a little bit. Let's go at some point xy. Well, what we'll often do is we'll write xy as a plus delta a, b plus delta b. And we assume we know f of AB, f sub x of AB, and f sub y of AB. So if we know those inputs, we can use that to approximate the value of the function nearby. So as an example, I did not choose a particularly nasty function. I wanted to do something that would be easy for us to just calculate. So let's say we want to do the square root of x squared plus 3y, and I want to approximate the value of this function at 4.1 and 2.9. So the first thing is we need to figure out what should the point AB equal. So is there any value of AB where we think we are close to the point 4.1, 2.9? There should be a natural one screaming at you. 4.3, right? And what would f of 4.3 equal? If I've done this calculation correctly, what would f of 4.3 equal? 5, right? I'm choosing a 3, 4, 5 triangle. But I decided not to write it as x squared plus y squared, just to have a little bit of fun. So we know what's going on at the point 4.3. And then the hope is if we know what's going on at 4.3, and if we know how it's changing in the direction of x, and we know how it's changing in the direction of y, we can approximate. What is delta A? What is delta B? So what would delta A equal? 0.1. What would delta B equal? I'm sorry? Not 0.01. Not 0.1. Negative 0.1. We're going down, right? So I wanted to choose one of them to be positive, one of them to be negative. Do you think the function is going to be larger or smaller than 5? Before doing the calculation, do you have any intuition for the problem? Do you think it's going to be larger or smaller? Or do you think it's going to be the same? So why do you think this? Why might it be the same? They're compensating. I chose it so that delta A and delta B are compensating. Well, it will only be the same if we think the partial derivatives are the same. Which partial derivative do you think is going to be larger with respect to x or with respect to y? I think with respect to x, we have an x squared versus a 3y, and x is a larger value than y. So my intuition is I think fx is going to be larger than fy. I might be wrong, but just looking at this, my gut feeling is I should get a number that's larger than 5. So we'll see if that's true. So now let's calculate f sub x. So that's the derivative with respect to x of the function x squared plus 3y to the 1/2. Yes.
So why would you expect it to be greater than 5 if the partial x is greater?
So if we look at what's going on, if we look at the approximation, the first term in the approximation is the value at AB. So that's 5. Then we add the partial derivative at f, the partial derivative of f with respect to x times the change in A, which is going to be a positive change. Then we add the partial derivative with respect to y times the change in y. Well, the change in y is negative, the change in x is positive, and they're the same amounts. So if the partial derivatives were the same, there would be no net change. So if I gave you the function x squared plus y squared, maybe the value would be the same. But since looking at this function, I think the partial derivative with respect to x is going to be larger than the partial derivative with respect to y, I think I'm going to be adding more than I subtract. And again, it's nice if you can have just some rough sense of what's going on before you do a calculation. So now we take the derivative with respect to x, we treat y as a constant. So this is just one-dimensional calculus. So I would just be 1/2 x squared plus 3y, and then we need the derivative of x squared. What's the derivative of x squared with respect to x? 2x. And this is really bad notation, which is what I just did here. And so I want to erase that. That was horrible notation. Why was that bad notation? I'm sorry? Well, one is I forgot the exponent. This should be minus 1/2. Yes. But when I wrote prime means what? It means derivative with respect to what variable? I should really be writing d by dx of x squared to remind myself I'm taking the derivative with respect to x. There's more than one variable in play. It's really easy to accidentally write prime. I started off, I was really good. I was doing d by dx, and then I forgot and I did primes. And I know that you know what you're doing when you're writing it up on an exam or a homework, but you've got to get in the habit of using the right notation. You will eventually make a mistake when you drop things. What's the partial derivative of x squared with respect to x? 2x. What's the partial derivative of x squared with respect to y? 0. So really what I should be writing at this point is not x squared. I should really be writing x squared plus 3y, because I'm really taking the derivative of that whole thing. And now I take the derivative with respect to x, I get 2x. The 2 cancels with the 2 down below, and I'm going to be left with x over the square root of x squared plus 3y. Okay. And so that's going to be my partial derivative. So what will happen if I put in the 0.43? Because that's the place where I need the derivative. I would get 4 over the square root of 4 squared, well, that's just 5. So I just get 4/5. Yes? Correct. So now I have to find the derivative with respect to y. So I'm trying to get all the pieces that I need. And so now I need to find what's the partial derivative with respect to y. So that would be d by dy of x squared plus 3y to the 1/2. So that would be 1/2 x squared plus 3y to the minus 1/2. Then d by dy of x squared plus 3y. What's the derivative of x squared plus 3y with respect to y? 3. So now the 2 is not going to cancel, and I'll be left with 3 over 2 times the square root of x squared plus 3y. And so now if I look at what's the value of the derivative at the 0.43 with respect to y, I would get 3 over 2 times 5. So that's 3/10 or 0.3. Right? To make everything easier, how might I want to rewrite 4/5? I'm sorry, 0.8, this is 8/10 or 0.8. And now, everything is going to be very similar. And so now I get my approximation. So f of 4.1, 2.9 is approximately f of 4.3 plus the derivative with respect to x at the 0.43 times the change in x, which is 1/10, plus the derivative with respect to y at the point 43 times the change in y, which is negative 0.1. So this would be 5 plus 0.8 times 0.1 plus, and now I would get 0.3 times negative 0.1. So 0.8 times 0.1 is 0.08. 0.3 times negative 0.1 is minus 0.05. I mean, is minus 0.03. So when I add them together, I get 0.05. So this would be 5.05 as my approximation. Okay. How far is 4.1 2.9 from 4.3? Anybody want to tell me how far I've traveled? Why 0.05? Well, the 0.05 is my new value of my function. I'm approximating the value of my function as 5.05. It is almost surely not 5.05. That's my approximation. I want to know how far have I traveled? How far is the 0.1 2.9 from the 0.43? So how would we figure out how far apart these are? So it's going to be the square root of 4.1 minus 4 squared plus 2.9 minus 3 squared. Right? That's how far I've traveled. So the first one is 1/10 squared plus another 1/10 squared. So it's 2/100, square root of that. So this is the square root of 2/10. Square root of 2 is about 1.4. Right? So this is about 0.141. Square root 2 is about 1.41. So we've moved about 0.14. Does that seem reasonable? Yeah, I mean, the x component moved about the x component moved 1/10, the y component moved 1/10. I've clearly moved at least 1/10. I've moved less than 2/10. 0.14 seems reasonable. Okay, so I did extensive calculations before class. I wrote it down. I'm doing it in Mathematica. The actual value of f of 4.1 2.9 is equal to 5.0574 ... So to get a sense of how accurate we were, it's a little bit closer to 5.06 than to 5.05. But essentially, our error is in not the like the 1/1000th place. Much smaller than the amount we're moving. We're moving on the order of 0.1, and the error is of size 0.01. It's a little bit less than 0.01 is the error. So the error is much smaller than the movement. So notice the error is much smaller than how far we moved. If I just said the value of my function is 5, is that an okay estimate? Yeah. How much is 0.05 out of 5? We're talking about 1%. So it's not horrible. It's not terrific, but it's not horrible. But when you're looking to see how big is the error relative to how much we've moved, we're saying that the value of the function is about 5.05. The actual value is 5.0574. Nobody here, I think, wants to take the square root of 4.1 squared times plus 3 times 2.9. Right? That's what we're approximating. So the idea is that we can use multivariable calculus to approximate very painful functions quite well. If we want to do better, there's a couple of ways to go. One is to find a better point to expand about. Well, we're not really going to find something better here. The second would be to add more terms. And this is why we did a little bit with Taylor's series already early in the semester. The more terms you take, the more accuracy you have, but the more work you have to do. And so you have to decide how much accuracy do we need to do? How much work do I want to do? If it's something that's extremely important, okay, you might want to be a little bit more accurate. You might want to make sure the bridge really will survive the amount of weight that's coming on. You might want to be very sure about what is the threshold. For other things, you might just need a rough estimate, and your order of magnitude might be enough. And so depending on what you need, you do different amounts of work. But this is a great application of calculus, is we can approximate difficult functions quite well by knowing some key points. And ideas like this were behind a lot of the old tables to expand functions. A lot of this is running in the background in different processes that are trying to estimate things that you then use for other things going on. All right. So any questions before we move on to gradients and directional derivatives? So we know how to calculate tangent planes. We just take more and more derivatives, evaluate them at the key point. We can use this to expand and to approximate. What we want to do now is we want to look and see how is the function changing in certain directions. Right now, which directions have we said are special? So right now, we've said a couple of directions are special. Which are the special directions? What do you mean by positive and negative? I'm sorry? Good. So maybe the x direction is a special direction. What else is a special direction? The y. And if we have a function of 3 variables, the z. Do you think the universe cares how you orient your coordinate axes? Can you prove that? If you can, please go to the philosophy department. This is way beyond my pay grade as a mathematician. Okay? I cannot prove or disprove what the universe cares about. I will act under the assumption that it does not care how I orient my coordinate axes. And so depending on how you orient your coordinate axes, you might choose different sets of variables. Again, what does New York or part of New York do very well relative to Boston? The grid in Manhattan. Do you have to orient things when you're giving directions in Manhattan relative to the east, west, north, south? No, you'd be an idiot if you didn't. You have this beautiful grid structure right there. You should be talking, go so many blocks east, go so many blocks north, and you'll get where you want to go. You'd be a fool not to use the grid structure if you're there. If I give you a sphere, what kind of coordinates should you use? Polar is a subset of what you should be using. But if I'm giving you a sphere, what should you be using? Spherical coordinates. If I give you a cylinder, what should you be using? Cylindrical. If I give you a circle, polar. And so depending on what I give you, different coordinates are going to be more natural than others. So when I'm writing my function down, when I'm writing in terms of x, y, and z, I've made these directions special directions. And I often talk about approaching the point along the x-axis, along the y-axis, along the z-axis. But there's other ways to approach. I could come in at a 45-degree angle. I don't even have to come in on a straight line. I can spiral. And so the whole point of directional derivatives is to say, well, what if I approach another way? And if a function is going to be differentiable, it shouldn't matter how I'm approaching. I should be able to get the same answer no matter how I do things. And so the first thing is we've talked about the gradient. This is the vector of partial derivatives. So if I have a function of n variables, the gradient of f would be df dx1, comma df dx2, all the way up to df dxn. And the idea is we just take the derivative with respect to each variable. If I were to rotate my coordinate axis 45 degrees and have new variables, then my function, the functional form would change. What it physically represents would be the same, but the functional form, how it depends on the variables, would be different because I'm now using different variables. I might be using x plus y as one of my variables and x minus y as another variable. So if I let u equal x minus y and v equal x plus y, how could you write x in terms of u and v? Okay, so x is going to be what? So what would x be in terms of u and v? If u is x minus y and v is x plus y, how could I get x? It would be 1/2 u plus v. If I just add them together, the y's are going to cancel. So x is just going to be u plus v over 2. What would y equal? V minus u over 2. Or maybe negative u plus v over 2, just to keep the order of the variables the same. And so if I give you something in terms of x and y or something in terms of u and v, I can pass back and forth between the two of them. Depending on what problem you have, sometimes one is more convenient than the other. We talked about the equation of an ellipse. And in Algebra 2, hopefully you learned how to do the equation of an ellipse aligned with the coordinate axis. I could give you an ellipse that's not aligned with the coordinate axis. This is something that is usually not done in Algebra 2. But once you learn linear algebra, you learn, well, I can just rotate coordinates. So let me just rotate so that it looks like it's aligned in the new coordinates. I'll write it down there, and then I'll rotate back to the original coordinates. And that's one of the things you learn in the next class, linear algebra, Math 250. You learn how to change coordinate systems to whichever system is more convenient for the problem you're doing. And so right now with directional derivatives, we're trying to say, well, look, if the function is differentiable, we should be getting nice limits no matter how we approach the point. This is something that's completely missed in one-dimensional calculus, because how many ways are there to approach a point? I can come from the right, I can come from the left. It's boring. I can spiral out, I can do so many different things in higher dimensions that multivariable calculus is a lot more interesting and a lot more challenging. So we start off with the gradient, which is the vector of partial derivatives. And now we want to use this to try to figure out how might the function be changing if we come along different paths. And so the first thing we're going to do is imagine we have some path r of t. I normally like to use c of t. Why do you think I like the letter c? P of t would be fine, P for path. What might C stand for? I'm sorry? No, I need some kind of geometric object that could be similar to a path that would begin with a C. A curve, right? I like C of t for curve. The book likes R of t for R is how far you are. And again, whatever you want to use is fine. I like to have things where I can just quickly look down and see what's going on. So for me, C of t, that means curve. That's where I am. Okay. So what we're doing is we're forming a new function R of C of t. So imagine we have some function and we have some curve in space. So this is my curve. And for each time t, so here's my interval, maybe 0, 1. I have some time t, and then I apply my map, and that gives me some point over here, r of t. And now I'm taking my function f. And so r of t, maybe I'm a function of two variables. Maybe this is x of t, y of t. Or maybe I'm 3 variables and I have z of t. I have a curve maybe in 3 space. Or maybe I have a curve in n-dimensional space. It's x1 of t, x2 of t. So you give me a t. I then go to an r of t, which maybe is x of t, y of t, z of t. And then I go from that to f at r of t, which is going to be f of x of t, y of t, z of t. And my function f takes 3 variables and outputs 1. My function r takes 1 variable and outputs 3. So the function f composed with r takes something with 1 variable and gives us something with 1 variable. It's always good to write down clearly, where are you starting, where are you ending? So my curve, it's a function of time. You give me a moment in time and there's a unique place where I am. If I'm talking about I'm driving from DC to Rochester, at 3 hours into my trip, I'm not at 2 different places. You give me a time and there's a unique location where I am. That location could have an x component, a y component, and a z component. I'm going up and down hills, through valleys, everything. And now my function f depends on 3 variables. It needs 3 inputs. So you give me a time, I'm giving you a triple in space, x of t, y of t, z of t, and then I evaluate my function there. But if I look at g of t, which is f of r of t, notice that g is a function from r to r. G is a function of 1 variable. We know how to handle functions of 1 variable. We know how to differentiate functions of 1 variable. And so we can apply one-dimensional calculus to the function g. Now, what makes this a little bit harder is normally when we do 1 variable calculus, everything in sight is a function of just 1 variable. But what we're doing is we start off with a function of t, we expand to a triple, where each component is a function of t, and then we feed that into a function f, which itself is a function of 3 variables. But really, looking in the background, we just have something that's a function of 1 variable. So we could just play the game very carefully, very slowly, and just consider g to be a function of 1 variable and try to figure out what is the derivative of g with respect to t. That's what this d by dt of f of r of t is. The left-hand side, f of r of t, is a function of 1 variable. But because f is a function of 3 variables, the idea is maybe there's a nice formula for the derivative of this function f of r of t in terms of the gradient of f and in terms of the derivative of r. Notice we have r prime. We don't have dr dt. Well, r is only a function of 1 variable, so they're using an abusive notation and writing r prime of t. You could write this, if you wanted to, as the gradient of f at the point r of t dotted with dr dt. To just be a little bit more explicit and remind ourselves that we are taking the derivative of r with respect to t, even though that's the only direction in play. That's the only variable in play. So this is telling us there's a nice formula for this linked function. Okay, so let's try to see why this is true. So we have g of t is f of x of t, y of t, z of t. So let's calculate g prime of t. That's going to be the limit as h goes to 0 of f of x of t plus h, y of t plus h, z of t plus h, minus f of x, y, minus f of x of t, y of t, z of t over h. All right, so does everyone agree that this is what the derivative of f is going to, the derivative of g is going to be? So we want to figure out what's going on. Well, imagine we didn't have the y and z components. It would just be f of x of t plus h minus f of x of t over h. That would look like the normal chain rule. And the normal chain rule, what's the derivative of, say, f, well, let's say the derivative of a of b of x. So maybe remember the chain rule, the derivative of a of b of x. So it would be a prime at b of x times b prime. So we have a little bit of a complication because we have all this other stuff going on. So what we can do is we can start playing some games. So we can look at f of x of t plus h, y of t plus h, z of t plus h, and then let's subtract off f of x of t, y of t plus h, z of t plus h, and then we have to add it back, f of x of t, y of t plus h, z of t plus h, dot, 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 over t. The dot, dot, dot is very important. What I'm going to be doing is I'm going to be adding and subtracting the same quantity. So I've added 0. Does that change anything? This allows me to focus just on the first part. Notice now that for the first two terms, they have the same y component. They have the same z component. Only the x component has changed. So if I look at just the first two terms, that's going to look like, say, f of x of t plus h, y of t plus h, z of t plus h, minus f of x of t plus h, I'm sorry, x of t, sorry, y of t plus h, z of t plus h, over, sorry, this should be h not t. So when you look at this, it almost looks like the derivative with respect to the first variable. The problem is we have f of x plus t. We want f of x of t plus h. We want the h to be outside the x of t. Then it would just be the derivative of the first part. I would be at the point x of t and I added h. Well, what I can do is I can play a little bit of a game. What I can do is I can multiply this by x of t plus h minus x of t, x of t plus h minus x of t, and I'll move the h over. So does everyone agree I've just multiplied by 1? I've just multiplied by 1. Why is this useful? Well, if we go back to the start of class today, we had 3 definitions of the derivative. If you look at the second, it's f of x minus f of a over x minus a as x goes to a. That's one definition. If you look at what I have right now, it looks like the point A is being played by x of t, and the point of x is being played by x of t plus h. And then we just have x goes to a is just h goes to 0. Okay. So I'm just trying to give you a sense of where this formula is coming from. If I multiply by 1 like this, what I have now in the beginning is looking like the derivative of f with respect to x with respect to the first component evaluated at the point x of t. And then I have the second piece, x of t plus h minus x of t over h, and I take the limit as h goes to 0. So now we have to see what does each piece go to. So as h goes to 0, what does this go to? I have x of t plus h minus x of t over h. What should that go to as h goes to 0? I'm sorry? Well, you're going to have 0 over 0. I've got x of t plus h minus x of t over h. If I gave you f of t plus h minus f of t over h, that's just the definition of the derivative. This is just the definition of the derivative. So this is the definition of the derivative of the function x. So this just goes to x prime of t. And over here, this is going to just go to the derivative of f with respect to x at our point r of t. And so if you look at what's going on, it's supposed to be the gradient of f times or dotted with dr dt. The first component of dr dt is x prime of t. The first component of the gradient is the derivative of f with respect to x. This is giving us the first component. And then you just go through the rest of the analysis and you see that everything is going to follow similarly. So this is the idea of where this formula comes from. It comes from just adding 0, recognizing what's going on. As a theoretical math professor, I have to tell you that there is one danger in this argument when I multiplied by 1. When I multiplied by x of t plus h minus x of t over x of t plus h minus x of t. What do I have to make sure does not happen? I'm claiming I can multiply by 1. What's the danger? That's not 0 over 0. Imagine I have a function where x of t plus h equals x of t for infinitely many small h's. Most good functions won't have that. Most good functions are not going to have infinitely many points which are arbitrarily close where they're the same. But if that were to happen, this would break down. So if you're really interested, let me know, and I'm happy to give you an extremely theoretical lecture. I'm not going to bore the entire class with it. You can fix that issue. This method of proof assumes that essentially x prime of t is not 0. If x prime of t is not 0, then you have some speed, and if you have some speed, you're not going to be equal in an arbitrarily small neighborhood. If x prime of t is 0, things break down. Well, but if x prime is 0, I'm dotting this with something that's 0, so it probably doesn't matter. So, again, I want you to be aware of when am I trying to slip something past you. Okay, given that I'm telling you I'm slipping something past you, it should not be too hard to figure out when I'm not being fully theoretical. Okay, but the idea here is we break it up and do component by component by component. We want to say, well, if I just keep the second and the third components the same, I'm just changing the first component. It's almost the definition of the derivative of f with respect to x. The problem is I need h to be outside the x of t. I don't want f of x evaluated t plus h. I want f evaluated at x of t and then add h to x of t. I don't have that. Okay, but I can get it pretty easily. And that leads to this formula for the directional derivative. And this is for an arbitrary curve. What's the simplest curve you can think of? Simplest curve. Simplest shape. That's a parabola. There's a shape simpler than a parabola. What's simpler than a parabola? A line. So maybe if I take the curve r of t is just some point plus t times v, maybe I'll get an even easier formula. And that is the very special, the directional derivative of f at the point p in the direction u, hk, is the following. So the first is we go through with the definition of the derivative. We take our point, we're taking our curve r of t, blah, 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 blah. But then it simplifies. And the reason it simplifies is imagine we're just taking r of t to be our point p plus t times the vector u. So this is going to be x of t, y of t. So if we take r prime of t, that's just going to be the vector u. And we're calling that hk here. That's going to be x prime of t, y prime of t. So in the special case when we're going along a straight line, I can write down a very nice formula for r of t. It's just my initial point p plus t times u. What value of t corresponds to starting at the point p? So what value of t on the line corresponds to being at the point p? 0. So when t equals 0, we're at the point p. And so from what we did before, if we let g of t be f of r of t, g prime of t is the gradient of f at the point r of t dotted with r prime of t. So for us, it is the gradient of f at our point dotted with the direction u. And that's where the directional derivative comes. It's talking about how much is the function changing. So if you think about it, it's basically saying, take the dot product of the gradient with the direction you care about. Can anybody give me a good direction we might care about? So what are our favorite preferred directions? So what's the direction we care about? Somebody give me a direction we care about. The x-axis. So, we could take u to be the vector 1, 0, 0. And that's going to give us df dx. So the directional derivative in the direction of x, not surprisingly, is just df dx. If we take u to be 0, 1, 0 in a shaka, that's going to give us the partial of f with respect to y. So again, whenever you have a new extension of an old concept, we have the directional derivative. Does this collapse to the standard partial derivatives that we've seen before? If we take the appropriate definition of u. If we restrict u to being along one of the coordinate axes, we should get back the original partial derivatives, and we do that here. One of the things that can make the subject a little bit tricky is I could take u to be something that's not unit length. And now I'm going maybe twice as fast or half as fast in a certain direction. What's the directional derivative? How does the directional derivative depend on the speed you're taking? Always take the absolute value of u's length to be 1. And if you do that, then you don't have to worry. So just always be taking a unit length vector in the direction you care about, and then you don't have to worry about, well, how do I adjust things because I'm now moving twice as fast in that direction? Is there a factor of 2 that arises? If everything is of unit length, you never have to worry about any of that. So just always, always, always take things to be of unit length. All right, so if you have any questions on this material, let me know. I'll save some time on Friday for a review, and then I want to talk about applications of calculus.